Hey, how you doing? Flipped Chemistry. You ready for another lecture? We are going to be jumping into the last lecture of this section where we're looking at liquids and looking at the properties of liquids and what they can do that solids and gases can't. So, unique properties of liquids. Liquids are cohesive. And we talked about intermolecular forces and intermolecular attractions last lecture, and we're going to be continuing that idea here where one molecule of a liquid is attracted to another molecule of a liquid, and they're attracted enough to each other that they want to stay near each other, but they're not so attracted that they're like locked up like a solid. So that allows them to move, but they move well in contact. Okay, it's not like a gas that it's moving, all over the place and they're not in contact. So cohesion, molecules of a liquid like to stick to each other. Co means, similar or of the same thing. That's a little different than adhesion, which we'll get to in a minute. Surface tension, because the molecules like to cohere, because they like to stick to each other, when they're at the edge of their fluid and they're interacting with the air above, they tend to actually hold tighter to each other at the surface of the fluid than they hold to each other in the body of the fluid. And so molecules along the top hold tighter than in other places, then that forms a layer, kind of like a skin of the liquid called a meniscus. Now the meniscus is just the same molecules as the liquid, but they're holding tighter to each other there, and they actually form a bit of a barrier. Okay, so that's the meniscus. There are chemicals that can break down the meniscus, and those are called surfactants. Surface, you can see the word surface in there, like the surface tension, and these are things that act upon the surface tension, so they're called surfactants. Okay, here's some pictures. So as this fluid is disturbed, you can see that the surface of the water moves as if it had a skin on it, right? And it does. It has this meniscus on top of it. And when the water is disturbed enough that it goes flying out into the air, it doesn't become a gas. It doesn't just poof into vapor. It comes out in droplets because the water likes to hold on to its fellow water molecules. So when it's kicked out, it gets kicked out in groups, and they still glop onto each other to form a drop. Okay, and here you can see again, the water isn't just laying flat across the grass leaf. It would rather be touching itself than touching anything else. And so it stands up on top of the grass leaf and forms water droplets. Okay? And that surface tension, that meniscus, is what allows water strider bugs to walk on the water. This is not how Jesus did it, right? This is how bugs do it. And they just spread their weight out over a large amount of water, and the meniscus is strong enough that when their body's weight is spread out over this wide area, the meniscus can just hold it. So they don't go right through into the water. Here's just a quick little demonstration of meniscus. I'm not going to show you the whole video, but what happens here is we've got a penny, and he's going to put a lot of drops on the penny, and it starts to get to the point where you look at this thing and you're like, wow, there's a lot of water on top of that penny, and it's not coming off. He's shaking the table, and the droplets still remain on top of the penny because they'd rather touch themselves than anything else. So it sits on the penny, but it piles up on top of the penny before the gravity and the forces trying to level this water out are able to overcome the meniscus. So really quite a lot of water fits on here before it eventually spills. Okay, it's a lot of water. Another quick idea, here's an example of a surfactant being done by a very cute little boy.
So, Max, today I'm going to show you how to make a boat, and it's propelled by salt. First, you need a piece of cardboard, and then you draw your boat on the cardboard. Make sure that the boat will have an opening at the back. That's where the soap will be coming out. Now cut your boat out. This is how it will look like. And now we're going to put some soap right here where the opening ends. And the soap will be the fuel. Put the boat gently on the water and then watch it go.
And the reason it's doing that is because the soap is a surfactant, and the soap is causing the meniscus to break apart. And as the meniscus breaks apart, it drives a little wave of destroyed meniscus. As the meniscus is destroyed, it makes a little wave in front of that, and the boat is able to ride that wave. So that's cool. It's just a neat example of a meniscus and the surfactant. Okay, so viscosity is a liquid's thickness. The higher the viscosity, the thicker the liquid. Okay, and so this has to do with, it comes into play when you talk about engine oil and things of that nature, right? You want it to be thick enough to stick to the parts, but not so thick that it slows down the motion of the engine. So the right viscosity for oil is important. Adhesion is the property of a liquid that allows the liquid to stick to something else. So cohesion, water or some other liquid sticking to itself. Adhesion, a liquid sticking to something else. And so adhesives like glue are fluids, liquids that have very high adhesion. They stick to other things, okay? And then capillary action is the tendency of a liquid to move up a narrow tube because of cohesion and adhesion. So here's how that works out. It sticks to the tube because of adhesion, and then it pulls its friend molecules up because of cohesion. And then some of them stick higher on the tube, and it pulls those friends up, and the level of the fluid tends to rise up in a tube. And the narrower the tube, the higher the capillary action will go. Of course, it's limited by gravity and the weight of the fluid, but again, the thinner the tube, the more capillary action you see. So let me show you some pictures. Water droplets hanging out with paper fibers, that's adhesion. Water droplets hanging out with each other, that's cohesion. It's just a silly little cartoon that helps you keep those two separate in your mind, okay? When you pour water, if you pour it too slowly, if you've ever had this phenomenon, you pour a glass and you're not pouring it fast enough, the water will adhere to the glass and run down the glass this way as opposed to coming straight out. And it keeps the water from coming straight out, and it pulls actually a good amount of water with it, defying gravity, along the cup, and that's because of adhesion and cohesion, right? And then this is just an example of capillary action. Here you have liquid in a tube, and where there isn't enough interaction with the tube for capillary action, this is the level of the fluid. Now you know that fluids seek their own level, and water in a hose would be the same level at all the points that it can be, but here it's higher than it is here because of capillary action. And as the tube gets narrower, the capillary action becomes more extreme, and up here the liquid is very high up in the tube as opposed to the reference level because the tube is much narrower. Okay, that's capillary action. Now meniscus, this is just a picture of the meniscus. Here you can see the shape of a meniscus and the actual thickness of it here on the water. This is a skin, it's just water, it's not another substance, but it's water that's more dense right there because it is highly cohesive and resisting contact with the air. Sometimes the meniscuses dip down and sometimes they go up. The difference is in a fluid that has high adhesion, it likes to stick to other things, it will crawl up the side of the tube a little bit, and the meniscus tends to be higher on the sides than it is in the middle. This is the kind of liquid that likes capillary action, right? In a liquid with very low adhesion that doesn't like to stick to other things, it will avoid the walls of the tube as much as possible. It'll actually be higher in the middle. So this is mercury, and mercury has very low adhesion, and it likes to stick to itself but not to other things. So its meniscus is actually convex, and the meniscus of water is concave. Okay. Phase changes. Oh, aren't we done with phase changes yet? No, we're not. You've been doing this since kindergarten. Here we go again. Phase changes are when solids turn to liquids, liquids turn to gases, solids turn to gases, gases turn to solids, all that stuff. There's some new terminology that we do want to introduce to you now that you're juniors and you've been in school for 11 years and you've been doing phase changes every year. We can finally introduce some new terminology to you. When a liquid goes to a gas, we would call that boiling before. Now we want to be a little bit more specific, and we want to say actually that's vaporization. vaporization can happen two ways. It can happen because of boiling, because of temperature increase, or it can happen at a low temperature because of pressure differences, and that we would call evaporation. So boiling and evaporation are just two sides of the same coin, and we call that whole process vaporization. If something vaporizes because of temperature, we call it boiling. If something vaporizes because of pressure, that's called evaporization. Okay, and you've already used those terms before as well. Gas going to a liquid is called condensation or liquefaction, and so that's just, again, you've used all these terms before. I can't believe I still have to teach it to you. I'm sure you didn't learn anything, but that's okay. It's all right. We're going through it. Here we go. Now, the reason we have to review that and get the idea of vaporization is because now we're going to introduce you to a concept called vapor pressure. So in my hydro flask here, right? Beautiful hydro flask. In my hydro flask, there is water level. And above the water, there is an airspace. And inside there, inside that airspace, there is water as well. The water has vaporized, and there are water molecules up in the airspace above the liquid. And when I first put the water in there, there was not as much water vapor above the water as there is now. And the water vapor has gone up and filled that space. And now the space has a high concentration of water vapor in it. We use the word vapor pressure to describe that. Vapor pressure is the fullness of the airspace with vapor from the liquid below it. And liquids will continue to vaporize into that space until it reaches a certain point where there's too much vapor pressure up there, and any more liquids, particles of the fluid that emerge out of the liquid state and into the vapor state will force other particles out of the vapor state back into the liquid. And so you've reached a dynamic equilibrium where there are still molecules of liquid leaving the liquid state and evaporating, but there are just as many molecules that are leaving the vapor state and recoalescing into the liquid. And so some are going up and some are going down, and it's happening at the same rate, and so we have a state of dynamic equilibrium. If I remove the vapor pressure, if I vent my hydro flask, then now it has access to the outside air. Now water vapor would move out the straw, and I would be able to have more water vapor fill that space. Okay, so it's the vapor pressure that would put a stop to the net progress of vaporization, but then venting that vapor pressure would allow it to continue. Okay, here's just some diagrams of that. Here's a sealed container. Here's an unsealed container. In an unsealed container, liquids are able to vaporize and then leave. And so you have vapors that are just going away and vapor pressure doesn't build up. In a sealed container, liquid particles are able to vaporize, but then they get so full up here that they start forcing themselves back into the water phase, and you have a dynamic equilibrium where just as many are leaving the water phase as are re-entering it. Okay, so that's just an example of dynamic equilibrium. Here we go, another picture. Some particles of liquid are leaving and becoming vapor, and that goes on until there's high vapor pressure, and then just as many start to leave the liquid state as re-enter the liquid state. Okay, phase diagrams. Here's the last idea. Phase diagrams show what state a substance will take at any particular pressure and temperature. And so it's a graph that has liquid, solid, and gas, and has temperature on one scale and pressure on the other scale. And as you find your place on the graph for whatever temperature or pressure you're at, you will see what phase the material will be. There's some cool things there. You can see there's something called a triple point, where liquid, gas, and solid come together, and you can have all three states of matter in the same conditions, and that's what's inside my hydro flask, right? Water at 0 degrees and at 1 atmosphere can be all three states. And so I'll show you that in a moment on the diagram. And then there's boiling points and critical points. A boiling point is the temperature at 1 atmosphere where the liquid is able to changes from a liquid to a gas. And then the critical point is the highest temperature or pressure at which a gas can be liquefied. Beyond that, it's not really a gas and it's not really a liquid. It's something that they call a critical fluid or supercritical fluid. And I'll show you an example of that here real quick. So this is water at 1 atmosphere, and at 0 degrees Celsius, we have the melting point or freezing point of water, and at 100 degrees Celsius and 1 atmosphere, we have the boiling point of water. And here's the triple point, where it can be a liquid, a solid, and a gas all at one time. I have ice, I have water, and I have water vapor. And that's what's going on in my hydro flask right now. This is the critical point. And the critical point is very, very, very hot. The scale doesn't continue up here, but this is like really hot. And at this point, what's beyond it in this region is called a supercritical fluid, because it has some properties of a liquid and some properties of a gas, and it's really neither. It's kind of a funky thing up there. Okay, and there you go. That's it. This is our discussion of liquids. If you have any questions, please post them in the comments field below, and I will get to them as quickly as I can, or I'll see you in class tomorrow. Jesus loves you, and so do I. Have a great evening.